thing that we want to learn is how we can just convert what we have learned up to this point into the control, right? So what we want to do, what we have done up to this point is what we call it prediction. And why this is prediction? It's because I give you a policy, right? I give you one policy, and I tell you that, okay, get this policy, go in the environment, play with it as much as you want, and come back to me, tell me a table, give me a table which includes estimates of the values or estimates of the action values, right? So you are fixed in the policy, you just evaluate that policy, right? So this is prediction because you want to just predict this policy, how does it work, right? But what we want to do in practice is control, right? So you don't want to just get the policy and evaluate it and come back to me, tell me that, oh, it's not a good policy, right? You want to, ignore any policy. You want to just go in the environment, start doing something, and gradually learn how to play optimal. Right? This is your final goal, right? This is what we call it control, right? Because you want to see the system is developing, and based on this development by this, in the states of the system and in the actions you do, you start to get feeling some sense about how you can play optimally. Now, one thing that you might tell me is that, well, you already told us about GPI, right? Generalized policy iteration. And this means that if we know how to evaluate a policy, we can always find the optimal policy, right? You just start with a policy, you evaluate it using the prediction algorithms we had up to now. Now you know the values, you can improve it, right? You just do the greedy approach, right? You just select the action which is maximum value. Then this new improved algorithm, get back to just evaluate it, and then you again improve it. You keep on doing this till you're over, right? Imagine that, just imagine that you want to get this idea of GPI and you want to implement it on a robot, right? What does it mean? It means that you need to give it a random policy. Every angle is just randomly moving, right? And this robot goes in the environment forever, like for years, to find out how exactly random moving going to look like. Once they understood, it comes back to you, you just improve it. Again, you leave it alone in the environment. And this is going forever, right? This is not something practical. On paper, it's nice because it's going to work, or theoretically, you the optimal policy. But this is not something that you are willing for, right? So what we have done up to this point is basically offline reinforcement learning. And offline learning, it means that you don't care about the number of samples you want to use, right? You only think about building one loop, one algorithm, which is going to find you the optimal policy, right? But how much samples you need, well, I don't care, right? As long as I can do it by sampling, I'm fine, because I'm going to get some samples, right? So this is offline RL. What we want to do, we want to do online RL. This means that I want to get my robot, and this environment, every single step that it takes, it's going to find out at least a bit of sense about what is the right action, right? And gradually, it's going to make its own way towards just acting normal, right? So this is a bit of, philosophy involved as well, because we as human beings, we don't try a policy billions of times to understand. Like the kid, when you teach it, when a kid learns to walk, they do not just simply start to just walk and fall down randomly and then start, oh, this was not a good policy. No, they start to just a step and then they fall. Then immediately after that, they're going to do the different. Not wait till they understand how exactly the policy works. So we as a human being, as intelligent creatures, we have online policy or online algorithm to just learn the policy. And this is the way that we do it. We usually sample the environment. We get some, modify a tiny bit what we want to do next, and we keep on going forward, right? Definitely, we put a bit of this is going to be rewarded, and so on, and so on, and so on. And then we're going to come up with a better solution. But at the end of the day, we do not wait till we are over with like the whole bunch of trajectories until we want to just improve or change our policy, right? Now, this is just a simple example that if you really want to just use offline RL, then for every single improvement in your decision, you need to just wait thousands of iterations, thousands of trajectories sampling to just start getting sensing. It doesn't make sense, really, right? And this is why we want to just get into a kind of algorithm, that this algorithm does not like simply work on a single policy. So it's going to ignore any policy, right? And then it's going to just sample from the environment. Every single state is going to do one action. And after doing that action, you're going to get a reward and goes to a new state, right? Based on this reward that it sees, it's going to improve its own policy, its own move, right? So we want to just end up with such an algorithm. And GPI in the basic form is not going to do the thing for us, at least for a practical environment, right? So this is why we want a control algorithm. And what we do, we basically just, again, do GPI, of course, but we try to just take this GPI to its extreme case. Like, let's get back to the GPI. So this was the GPI algorithm or approach. And the idea is that you start with some policy. And then as long as your policy is changing, you're going to evaluate that policy. You get the action value function. And then based on that action value, you act greedy, right? And by acting greedy, I mean that you look at the action value function. And then you would say, well, for this particular state, the best action is this one because this is having the largest estimate of the value, right? And then you're going to do that action, right? And you keep on going like that, right? So this is the GPI algorithm. And this was the greedy approach. So when you want to update your policy, you would look at the evaluation that you had. This is the prediction you got. This is, for instance, is given to you by TD lambda. And then once you did or perform TD lambda on your policy pi, then it's going to tell you in a particular state, doing one particular action, what is the value, right? What is the estimate of the value? Now you are in particular state S, then you're going to just look among all the actions that you have. You take the action which is giving you the maximum value, right? So this was the approach for updating. And now what we want to do, we want to just make it online. So what is the most basic approach that you can say? You can say that, well, yeah, I think this is, again, a story. I'm sorry that I'm being so storytelling, but I think I want to just say the same story as I said before. So it simply says that this is not efficient, I told you, right? So it's OK that I go for the next slide, right? OK, so now, but how can we just make this GPI online? Any idea, any suggestion? Can I just do this GPI simply online? When you are evaluating, what do? You go on a trajectory always, right? When you do use TD or Monte Carlo, whatever the approach is. And every single step that you take, you see a new sample, right? And based on that sample, you update your values, right? Or your action values, right? Correct? Do you agree? OK. Now that you update it, if you are using GPI, you're not going to do anything. You keep on going and updating, right? So you keep on playing with the same policy as before, and you collect new samples, and you keep on improving your update, right? But why we should do that? Maybe when we update, right, we have a new action value, right? Everything got updated, right? We just use that very bad estimate to just improve our policy, right? And then for the next action, we don't act with the previous policy. We act with the new policy. It makes sense, right? So if you just, if a child just starts, next time that they stand, they do not walk the same as before, right? They try to put this step differently, right? So they just got one sample falling, it was a very bad reward. Based on that, they estimated that it is not a good move. So the value of that action state pair just went down. Now, a new action, which is just putting your leg differently, is going up, right? And they are doing it differently. Again, they fall. They do not do any of those moves they have done before, right? They do the third one. And they keep on going until they can just take the first step, right? And then again, for the second step is the same, and right? So the main idea here is the one, right? So this is the control algorithm. This is eventually GPI. The only difference is that your GPI is not doing any evaluation, really. It just uses single time step to update the action values, and then it's going to use it for so what you're doing, so I'm talking about the general algorithm X. So X could be Monte Carlo, it could be TD, anything, whatever algorithm you use. Just think about TD lambda, the most general one. So you're going to put that algorithm. This is able to just do prediction for you. It's able to evaluate your policy. So you're going to give your policy to this guy. This guy is going to one time gets from one state to another state, and immediately when it's in the new state, it is able to update this action values. It's going to update, right? So it's going to say that, okay, I'm in the new state. I got all the action values changed, and then I am going to update my policy based on action values. And converge, actually. I'm going to show you, yeah. But there is a bit of trick here. I mean, eventually converging is going to converge. But your question might be, does it converge to the optimal policy, right? Then we need to just add epsilon here, right? We need to make it epsilon greedy, right? But I'm going to explain. This is the whole, this part, of course, is whole about this, right? But it's a valid question. This one is going to converge, definitely, but it is not necessarily going to be the optimal policy. So we're going to talk about that. Questions? No question? So basically what we are doing here, we are having one pair of action values, right? So you're in one state, you do one action. This guy, policy pi, right? So now that you play with this policy, you got that action. This is your action value that you had before. You're going to sample one particular sample return, right? If you, for example, use TD0, you're going to get into a new state. The value of that new state is going to give you the sample return, right? So you're going to compute this sample return. You're going to update this guy, right? So now that you updated this guy, this action value has changed, right? And if you are, for example, thinking about the case where you're using TD lambda, not only this action value is going to change, everybody who has happened before is going to change, right? And now, given all of these new action values, you can just update your policy, right? You would say, okay, this particular action is not anymore giving me the maximum value, right? So I'm going to change to the one which is giving me the maximum value. Everybody's cool? Questions? No question? Okay, so now this is a very valid question, so it sounds totally random, totally loose. The point here is that, well, you can eventually converge to something, but you cannot guarantee that this guy is necessarily converging to the optimal policy. But we have a trick to just make it converge to the optimal policy as well. So we're going to see that. The key point is that GPI, I mean the policy iteration, as I told you before, this is very robust against the error in the evaluation, right? So if you just do a couple of iterations and you terminate it, even though you don't have the right values, but it's going to converge eventually. So based on this idea, this one is also going to converge, but it needs a bit of improvement, okay? Now, if you got no question, we write down the control loop for one particular approach of estimation. and then this is going to make things much easier, much clearer. Okay, so Monte Carlo, that guy is the easiest one, right? Because you don't need to think about the TD, the next state, no Bellman, no such complications. So the only thing that you need to look at the whole trajectory, right? And then you want to just you just collect all the rewards you have collected. This is your sample return, the easiest one, correct? Now, this algorithm that you see here is eventually the Monte Carlo algorithm that we had before, right? So you have this episodes 1 to k, so multiple episodes. You just start with a random pair, and then you go on a trajectory, right? And this trajectory, well, you're doing it with a policy pi, right? Right? So you are just doing it with a policy pi, and then you get this one. Then from this one, you jump to another one till you get to the end. And now if you want to update, well, you're going to say, OK, this guy, the sample return is anything in future. So this is going to be G. And then I am going to take this G and update my action state pair, right? And then you go for the next pair, and so on and so on. This is the way that you evaluate. You update your estimation action values, right? Now, if you want to do it or convert it into a Monte Carlo loop, the thing that you need to do is that every time that you are taking a new trajectory, you just update your policy. So what does that mean? This means that, let's say I am at the first episode, so I just collect one complete trajectory, right? And then going over this trajectory, I just update all the values, right? So Q has been updated. In my table, for different action and states, I have different values. They are not best estimates ever. They are actually very loose estimates initially, but that's OK, right? Now, I want to go for the next trajectory. I want to sample the next trajectory. If you just do Monte Carlo evaluation, you basically keep with the same policy, right? Correct? But now you're going to update your policy, right? What you're going to do, you're going to say, OK, I look at whatever I ended up as the Q function here, and then I give it to my greedy algorithm. It's going to give me a new policy, right? When I want to sample the next trajectory, I am going to just sample with this new policy. Everybody's clear? So the first trajectory was sampled by one policy, right? And then you got some idea. Now you would say, OK, this very bad estimate tells me this action is better than this action, right? So next time that I want to sample, I am going to sample this guy, right? Whenever I'm in this state, I'm going to go this way, right? And then you make this new policy, which is the greedy version out of your estimate, and then you sample your next trajectory, right? Now that you go on the next trajectory, you're going to see a bunch of new states. You're going to see some previous states again, and you're going to update all of them, right? And then you get a new action value function. Again, you go to line 4, you update, then you sample the new guy, right? And you keep on going like this, right? Now, what is the change compared to evaluation? Well, you don't need to wait forever, right? So you just need to sample one trajectory. You get some rough idea. You start again, right? It's like you play a game, and after playing the game, you just lose. You say, OK, this was a mistake, so next time when I get here, I'm going to do another move, right? And you again play, right? And you keep on playing. If you play so many times, then eventually you're going to just see every possible state, and in every possible action going to get somehow tested. And out of that, you're going to understand what is the right policy. Everybody's cool? Questions? Yes? With a single, right. Somehow, yes. Yeah, it's eventually Monte Carlo evaluation with only single trajectory is the same thing, right? Question? Yes? Yeah, we don't do it. We really don't do it even. We are going to do TD, right? I just wanted to give you the idea, but this is a valid challenge. So if you have really no terminal state, you actually cannot really rely on this one, right? Because you can truncate, but then you need to again have a long trajectory and just don't use the last parts, right? Make sense? Okay. Yes?
What's the benefit of initiating with a random state action pair for like each trajectory comparing to always starting with the same?
Well, right. What is the benefit? Well, yeah, I mean, typically, I guess I shouldn't say random. I mean, it doesn't impact, but one other way that you can do it is just you generate random state, and then you play even your first action with your policy. You can do it. But this is not going to change too much. But what is the benefit of starting from a random state? Well, the benefit is what you're going to see next, that you are not going to get locked into one particular path, right? But this is not enough. We need to add to this.
In the original Monte-Carlo action value evaluation, did we also start?
Right. Yes. Yes. Yeah. Because we just want to know what is the value of your policy, right? So you need to start from a random place that you just go towards and like play randomly or play with your policy in the environment, right? You can not always start from the same one, right? Because it might be that this guy is just next to the terminal state, right? You're going to only learn the value of that state. Right? You never get the chance to just get the other action unless you really play with the random policy, right? Well, depends whether you have initial state or not, right? So you do not necessarily have initial state, right? Now, for a game, you have, right? But if you're thinking about like a robot, it's not necessarily the case, right? Yeah. Questions? No question? Okay, so if you got no question, then yeah, let me just finish this part and then we're going to have a break. So if you compare Monte Carlo evaluation with this one, so it's basically just you do in-loop greedy improvement only in line 4, and this means that you're going to use one sample trajectory to estimate. Very bad estimate, but that's okay. You're going to use that to just improve your policy, and then you use that new policy to just sample your environment. Okay, so now let's get back to this big question. So does it converge? Okay, if we do this one, does it converge? The answer is that not really. Can you think of a case where it's not going to converge? You remember this guy we started with, right? This was the robot, and then I wanted to just find out which guy is paying more, right? And then what if we are doing here? What do you think? What's going to happen? Let's say we have this robot. We have company A and company B. I guess company A was paying more in average, right? Okay. So company A was paying more, and now this guy wants to just use the control approach that I told you to just find out where to work, right? So what it's going to do, it's going to start randomly and say out of bad luck, it starts with company B, okay? In the random choice, first choice, it's going to choose company B. Now, when it just works at company B, it's going to get one reward, right? And the reward is, say, $150, okay? The first day payment is 150. And then it gets this one. Out of this, it's going to update its action value function. It says that doing this action, doing the action of going to company B, is giving me 150. Company A, I don't have any sample. It's going to remain 0, right? Now, next time that it wants to play, what it's going to do, now look, I mean, it's not going to, again, keep sampling randomly the environment, right? It's going to improve the policy, then it samples, right? So you're going to say A or B, B 150, A 0, B, right? So it's going to go working for B again, right? And so on for the third day. And so you're going to get stuck with company B simply because it is started with company B, right? If it starts with company A, it's going to be the same thing with company A. Yes? Here you don't have any state, actually. Action, right? You just randomly choose your action, your first action, right? The first action, right? And then for the next, I mean, each time that it's just going to one company, I'm considering that one considering this one trajectory, right? So there is no state. The problem is super simple. There is no state here. The only thing is that you have two actions, A or B, and you want to choose, right? And then you're going to choose B, right? Now that you do, so this is why I put a state empty, right? There is no state here. So you go for company B, your trajectory is over, right? Now you can update your action value, A and B, right? And then the A and B, I mean, your action value function has only two different values, right? State empty and action A, state empty and action B, right? And you have only a sample of action B, so you're going to update that one. Action A has not happened, so you cannot update it, right? So it's going to remain 0 if you started with the initial value 0, right? It converges, right? It converged actually after the second one, right? But it converged not to the optimal policy, right? So it just converged to the one converging point, right? Yes. Yes, yes. But it's converging, right? So it's just doing one thing forever, right? But this thing is not necessarily the optimal thing. Yeah, this is what we do in epsilon greedy, right? This is the next thing, right? Yeah, yeah. This is. I just give you the reason why, or you get the intuition. What is the problem here, right? So the problem here is that if you just keep on with this this control loop, greedy control loop, or just relying on those few samples, and then this can just stick you with a bad solution. Simply you don't get any samples of A, right? Everybody's clear? Questions? No question? Okay, so this is what's going to happen forever, so this is not a good idea. One thing else that you could say that even if I, for example, randomly just once or twice, randomly make this agent to work for company A in future. Like you start with B, going to work with B over and over and over. And somewhere in between, I just say once, just go for once to A, right? That sample from company A would never give it like, it's very low chance that that sample from company A going to give it like a larger estimate of the value, right? Because it could be that it goes that day to A and A gives just for that day it pays low, right? So if it really wants to get the idea what is the right choice, we had it at the very beginning of the course. It has to play enough number of times for A and B so that it gets a good estimate of both cases, right? And then based on that, now it can build its greedy algorithm, right? So that is the issue. This is the issue that we say this algorithm is actually having lack of exploration. This is something that could happen if you just stick to the greedy approach, meaning that you start with one stage, right? And then out of first random policy, you start to get one path, right? And that path is going to get some estimate, non-zero estimates, right? Whereas the remaining guys in the gain 0, right? Now, next time that you want to just play with your greedy policy, since you are just taking the actions which have higher values, right, you're going to somehow stick to what you have done before, right? Because most probably they are better than nothing, correct? So if you want to get from 4 and you walk, you finally get to that 4, right? Now, if you just update these steps that you have taken in between, all of them are non-zero, whereas any other location is 0, right? Next time that you want to move, if you are, you're going to look at this and say, okay, should I move this direction or but is non-zero, you're going to again go that direction, right? It's like you do a mistake and you keep on doing that mistake forever because you only know about the reward of that mistake. You don't know about the reward of other things. So you are not exploring the environment. You are just exploiting. Right? So this is the challenge. You're only exploiting, you're lacking exploration. If you want to get rid of that issue, so this is the key downside of doing greedy improvement. The greedy improvement is just going to exploit the knowledge that you have collected, and that knowledge is going to quickly converge to something from exploring the rest of environments, right? So this is a challenge. How you can resolve it, you need to just add exploration to that, right? So maybe this is, okay, this particular path is taking me to the door, right? But maybe I can try another path, right? So when you are doing greedy, it's like you're afraid to do anything else. Like, oh, I just got to the door, and that's it, right? So maybe I should take it forever. I don't want to explore anything new, right? But maybe you can take another path, right? And maybe this path is going to take you again to the door with a better, with lower time, right? So you need to add some exploration to that. And how we can do it? Well, basically, this is the epsilon greedy, which we are going to talk after.